further ado, I think I will introduce our first speaker. So our first speaker is Professor Claire Adjiman. She's from Imperial College in London. Her research interests are on multi-scale process and molecular materials design, including the development of design methods, property prediction techniques and optimization algorithms. So Claire's going to talk to us about some of her work on digital solvent design for accelerated process development.
So yes, indeed, I want to talk a little bit, give you a very brief overview of what we've been doing on digital solvent design. So of course, we all know why solvents are important. They impact all aspects of process and product performance. We can start from the physical properties and how solvents or solvent blends impact on solubility of APIs, but also think about synthesis and the fact that by just changing the solvent, you can completely change the selectivity of a reaction. So it's a really important variable in manipulating the performance of your process. But it's not enough to look at the molecular properties. We really need to understand the process impacts, and that impacts many different KPIs. And so we're looking, for example, at process safety, the quality of the product, the productivity of the process, the carbon footprint of the process, and so on and so forth. And this link is becoming ever more important and challenging as we look at new modalities. So for example, this is some data on oligonucleotides. Depending on the oligo, you're looking at process mass intensity values of around 150 to 200 per nucleotide. So really, really high values, which are in large part driven by the choice of solvent that is being made. So given this, we'd like to develop a digital solvent design platform, and here are some of the things we're hoping to achieve from such a platform. We'd like to minimize material use, so to be able to make decisions at early stages when we don't have that much material available. We want to reduce the time and cost of process development by reducing the number of experiments. There are also implications, as we'll see, for safety in terms of the safety of developing the process. But more importantly, so these are all things you expect from sort of digital design, it also gives us the opportunity to connect the solvent and the molecule to the process, and that's something that can be quite difficult to do in experiments that are focused on very specific aspects. So what we want to think about is these solvent-process interactions. So we cannot just decide on a solvent without thinking about the concentrations, the temperatures, etc. in the process. They are connected in an interactive way. And doing these things digitally allows us to look at these connections. And the other aspect is that it allows us to look across multiple steps. So to think about not only the reaction solvent and the crystallization solvent separately, but how these interact and whether we can avoid, for example, solvent swaps, how perhaps making some compromises in some of the steps leads us to better overall performance. And these are things that we can only explore through digital design because we can look at this large space and this whole system perspective. So what we'd like to get out of digital solvent design is, first of all, a prioritized list of solvents and process conditions or options to be investigated. So we are really guiding experiments. We're not coming to a final design. It's far too early when we're looking at so many possible molecules and blends to make some final decisions. We also want to get some insights into the trade-offs in the process and to understand better what those trade-offs are. And we want to be able to explore solvents or blends that are beyond the usual suspects, to consider green or novel alternatives, deep eutectic solvents, what have you, to look at what the benefits might be. So what we've been doing is developing a framework to try and put this on a unified basis and to be able to keep expanding that framework going forward. And so we start with a design space of something that we have to define, which is what molecules, solvent molecules or atom groups we're willing to use in our design. One or more reaction routes if we're looking at reactions, and specific units or a choice of units, flow sheet designs, connectivities of flow sheets. So we can make that, we can just focus on the molecules, or we can expand the set of decisions we're willing to consider. And then we need some KPIs that relate to product and process performance. And from that, we want to achieve this rank list of candidate solvents and solvent blends, process conditions, and so on. So the platform we've been developing to do this consists, first of all, of models, as you'd expect, that connect the molecular scale to the KPIs. And so you can distinguish sort of three elements to that. First, you have structure-property relations that give you your thermodynamic properties, phase equilibria, kinetics, growth, etc. Then you have process models for your unit operations and larger systems, and then the performance metrics that go from process conditions, amount of solvent, and so on, to sizing, costing, and other metrics like safety indices. You can do life cycle assessment with all the data that you're generating from these models. And wrapped around this, we use optimization as the tool to explore the space of possibility. So we don't want to be evaluating every possibility. We want to search that space in an effective way, in an efficient way. So we develop optimization algorithms. We use concepts from mixed integer optimization because we have discrete decisions: what solvent, how are the units connected, which type of separation unit are we using. And we also use optimization under uncertainty, which enables us to get robust decisions to the things we don't know. So that give us, for example, best average performance in the presence of uncertainty about impurities in the system, for example. So these concepts are used to obtain these lists of candidates that we're looking for. Just looking a little bit deeper in terms of the models that we're using. So we're a little bit agnostic in that. Where we have first principles models, we like to use them because they don't require a lot of data. So we use all sorts of things like quantum mechanical calculations with continuum solvation for kinetics or models of crystal growth. We use thermodynamic models like GSAFT or UNIFAC, mass and energy balance models, and we use these concepts from superstructure representation for the molecules and the flow sheets. And then where we need to, we use data-driven models, and these might be either driven from experimental data or from computational data, so it might be surrogate models and group contribution methods, and we use model-based design of experiments to reduce the number of experiments that we need to carry out. So just to give you an example of recent work in this area, we've been developing an ANN classifier that enables us to predict the probability of a mixture giving a single liquid phase or two liquid phases. So in this case, we have an API water ethanol system, which water ethanol as a solvent is in a single liquid phase, but in the presence of API may separate into two liquid phases. And we basically, our classifier gives us a probability map of whether we would form two liquid phases. So here, what you have is maybe I'll use this. I don't know if I just need to get the pointer. What you have in the middle is an area where we have liquid-liquid equilibrium, and we even have a solid-liquid equilibrium, and so that's light-colored. And then in those areas we have either solid liquid or purely liquid phase present. And so we can either avoid liquid-liquid if we're in a crystallizer, or we can design for liquid-liquid extraction, for example, if we want to. So we can put these as constraints, and it's very cheap to evaluate this model within the optimization framework. So now I want to give you a few examples of how we've applied digital solvent design. So first of all, in specific units, so in reaction solvents, we've been looking at suppressing the generation of hydrogen cyanide as a side reaction to amino acid activation. And we've been using this optimization-based methodology where we have to use surrogate models, because to quantify the solvent effects on reaction kinetics, we either need to use experimental data. So we don't want to generate too much of that, especially when we have HCN formation, or we need to use QM-generated data. So in this case, we've used QM data. So we start with a small set of solvents. We do a few QM calculations to predict the rate constant in those solvents. And then we build a surrogate model that enables us to predict what will happen in other solvents for which we have not done QM calculations. We then use this model, which is actually a multilinear model, so it's very simple. It's a very simple model in a computer-aided molecular design framework, and that enables us to identify the best solvent or a set of best solvents. If we have already done the QM calculations for those, then we can terminate and move on to experimental verification. If we have not done this, then we do more QM calculations, and so we're kind of exploring the space for the QM calculations and keep going around this loop. We've used model-based design of experiment to decide where to start in our, with our few QM calculations. And we find that with 7 to 15 solvents, you can build some very good, reliable models that enable you to really identify the best solvents, where we are able to explore thousands of potential solvents if we want to. So we can restrict ourselves to the usual suspects, or we can go much beyond that and predict what would happen in thousands of different solvent molecules. So in terms of our particular case study here, we've done this for a few case studies, but for this one here of amino acid activation, we did these calculations in 13 solvents, having explored the mechanism for HCN formation and the mechanism for amino acid activation. And then from this, we're able to generate a map of solvents. So here you see we're trying to maximize amino acid activation and minimize hydrogen cyanide formation. So we want to be in this corner. There is no solvent in this corner, unfortunately. But what you have in red are solvents that give us the best compromise between those two objectives. So the Pareto front in multi-objective optimization speak. And then the kind of standard solvent is shown here in this black dot. So all of the solvents in the red box are actually doing better than the standard solvent, and they're all up for experimental exploration. So that's one way in which we've used digital solvent design. Then looking at crystallization, we've also looked at the trade-off between yield and the shape of the crystal, so the aspect ratio. So we have a simple thermodynamic-based models, but we integrate the model of Tilbury and Doherty for crystal growth in this. We look at initial and final temperatures and choose one solvent from 21 possible solvents. If you try to optimize only one of those criteria, you find water gives you the lowest aspect ratio, and heptane the best yield, but you're also able to identify the trade-offs here. Okay, as these are trade-off solvents, and there are many other solvents around here that are not shown that will give us worse performance than any of these Pareto points. And then we've been taking this to end-to-end consideration, so integrating using the fact that we're using the same platform to go from synthesis to crystallization, washing, drying. And so we've built models of all of these, and we look at a range of KPIs. And so very briefly, we've looked at this for methanoic acid production, where we're looking at things like the solvent E factor versus purity, and get the Pareto front, looking at safety indicators versus, again, process E factor or solvent E factor. And you can explore all of your trade-offs. Each point is different solvent and process conditions. We've also started looking at route selection in this context. So here, a very simple case where we have two routes to make 4-nitrophenol, two-step reactions, two-step routes. We use the same step repeated in terms of the flow sheet structure. And you again get here, we have energy consumption versus process E factor for the different routes. And so you can get a very early assessment of the challenges of these different routes, and that can guide your choice. In terms of our current direction, so we are trying to expand this to increase the number of steps we take into account, look at solvent recycling, and enable different structures of flow sheets to be optimized. So should you use crystallization? Should you use a different technology, et cetera, et cetera. We're looking also at the role of high throughput experimentation, so trying to integrate this in the framework in order to have more data-driven elements to it, and then to broaden the scope to predict a broader range of properties in the absence of data, and to integrate with reaction network models in terms of route selection. I'd like to end by thanking all my collaborators at Imperial and at Strathclyde, and thank you for your attention. Thank you to the sponsors as well, and I'd be happy to answer any questions.
Thank you very much, Claire. That was excellent. Does anyone have any questions for Claire? Sorry, Richard.
That's very interesting. I was wondering when we future systems tools that could make the solvent systems too, or it's always just simple solvents.
Yes, so in the end-to-end work that we've done, we've looked at mixed solvents. So you can start with a mixed solvent in the reaction synthesis. You can also consider adding an anti-solvent in the crystallization. So the optimizer decides for you whether you should use a temperature to drive the crystallization, or anti-solvent, or a mix of both, for example. So it really depends on the availability of models, and I think that's where physics-based models are really useful to look at mixed solvents. We have those for solubility. We don't yet have those for crystal growth, and we don't yet have those for reaction kinetics. So we're looking at solubility in the reaction as well.
We've got a question coming through the app.
Yeah.
This is from Peter Hollowell. It's asked, is sustainability of the solvent built into any of the models where there are multiple options?
Yes, so that's a choice of KPI really. So the fact that we're looking at E-factor, we're looking at the, for example, the GSK indicators. We haven't yet hooked it up to a full life cycle analysis, but that's something that we very much want to do.
Alistair.
Just wonder to what extent you've taken form into account in this when you're studying the solvent space and solvent formation.
Yeah. So currently we're just assuming a single crystal form. So the crystal data of other solvents, so form and the melting point and heat of fusion of that form is always an input to what we do. There's no reason why we couldn't extend the model. If you have that data for different forms, then you can build a phase diagram and we would be able to then identify which form is being obtained depending on the solvent. Yeah. But you would need that solid state data, which is why one of the big challenges is to try and get that in a more predictive way. But if you have that data, definitely we can build a model to handle that.
Okay, I think if there are no more questions, we'll
Thank you.
go. So thank you very much, Claire.